Welcome. So in this video we'll learn what is separation of roots. Okay, so until now we have learned to solve polynomials up to degree 4, right, by different methods. But for higher degree equations it is not easy. So we can't do the direct approach, so we'll do something else. Okay, so and that the new way of doing is maybe easier for the smaller degree also polynomials. So we'll understand this concept by only considering real coefficient equations with real roots. Okay, we'll study using these equations. So first what we have to do is, as the name suggests, separation of roots. We have to separate or isolate, okay, both are correct, the root. And what does that mean? If we can find an interval containing that root and no other, okay, meaning if a is the root and x comma y is an interval and a is inside this, and if b is a root of a given polynomial, it should not be in this, it should not be there, then a is isolated. Okay, a is the only root inside the interval, it could be any interval. So that is the meaning of isolated root. Okay, so now for example, if you consider this equation, okay, if you consider this equation, each contains one root. Okay, each interval will contain one root, so they are separated. Okay, so how to isolate that root? So for this we have first to know how many real roots, right? How many real roots are there for this equation? Then only we can separate them. And also how many of them between given two numbers. These all concepts we should know. For that, sign of polynomial is important. What is sign of polynomial? If we put some values, say 2, if we are getting a negative number, then that polynomial sign is negative for this particular value. And if we are getting a positive value, then for that we are getting a positive. Okay, now we are trying to find the sign of a polynomial when the value of variable x, here x is there, right, when the value of variable is very small. Okay, I think small, and both sign of polynomial for small as well as large values of the variable, here x. Okay, for that we will need a result, so we are considering that. So consider a polynomial of degree n, and this is, we are assuming that all are real with real coefficients. We are taking the modulus with the triangle, you know triangle inequality, right? A plus b, the modulus is less than or equal to mod a plus mod b. So similarly we will split into every term can be splitted like that, less than or equal to, and we are taking this mod of x as r for simplicity, so we will get something like this, and mod of c1, mod of c2, etc., mod of cn. Okay, these will be some numbers, right? If we are taking the maximum of these numbers, then that this equation will be again less than or equal to c, that is c, the maximum is c, suppose maximum is c, then c, it will be, this equation will be less than c of r plus c of r2 plus c r3 etc. CRN, right, because these are big. so that will be again big. So taking C common, we will get this expression. Okay, so this is R is very small. Suppose R is very small. Okay, taking less than 1, meaning X is very small. We will get this term is what? Geometric series, right? And sum of geometric series, you know, A into, right? We will get this expression, and this is clearly less than this, right? We are R minus Rn plus 1. What is that? If you take R outside, this is R into 1 minus Rn. This is the expression actually. So this number is less than 1. So R into a less number, we will get a less smaller number when compared to this. Right? This will, if R is say 2, and this will be some 0.5. So 2 into 0.5 is 1. So 1 by 1 minus R is clearly less than 2 by 1 minus R, right? So similarly we will get that. Okay. So this portion became R into 1 minus R, so we will get mod of f of x is less than or equal to, less than, by less than, here it is less than, so less than C R by 1 minus R, provided R is less than 1. Now this is very small because R is very less than 1, so we are taking this value as less than epsilon, where epsilon is a small positive value. So rearranging this, okay, we can write this as R less than epsilon by C plus epsilon. And see, epsilon by C plus epsilon, this number is greater than epsilon, so clearly this is less than 1, right? 1 by 2, if the denominator is greater than the numerator, it will be less than 1. Okay, so let me rub this for a second. Okay, so we will get this is less than 1. Okay, and clearly this is less than epsilon, so f of x, modulus of f of x is less than epsilon. And from here, this is mod x, so mod x is less than epsilon by C plus epsilon. What does this imply? When mod of x is very small, f of x, the value of f of x is also small. Okay. Now from that we will understand some conclusion. We will make some conclusion. Suppose x is very small, sufficiently small. Okay, x is very small. Then this is a polynomial of degree n. Then the sign of this polynomial is equal to the sign of this constant. That is the only result you will have to learn. What is that? The sign of this polynomial will be sign of the constant when this x value is very small. How you got that? That is the proof here. But this is the result you have to learn. Okay, we'll just understand how you got. Since x values are very small, okay, we'll take k naught to from every term. Okay, so we take k naught common outside. So this k1 might not have k1 common, right? So we can divide. We can do that like this, right? So this is our C. See, new term, coefficients. they are of the form ki by k naught. Okay, I'll give you an example. Suppose 2 plus 3x plus 2x 2 is not, I'll do 5x square. Now if we are taking 2 outside, this will become 1, this will become 3 by 2, this will become 5 by 2. So this is our new coefficients, that are C1, C etc. So consider this term only. Okay, these terms, as x is very small, these terms are less than 1. Okay, these terms are less than 1. So 1 plus a smaller number, even if it is minus, it won't, this term will still remain. This is less than or equal to 1, right? So 1 plus or minus a small value less than 1 will always remain positive. So this part is positive. So the sign of phi of x depends upon this constant. Clear? So that is the first result. Now the second result, again, for suppose that the coefficients of this x powers are not all 0. And the sign of the we consider the sign of the polynomial of this polynomial where it is arranged in ascending order, meaning increasing order. So what is the sign? It is it depends upon this lowest. This is the smallest x power term, right? It will depend on that. For the sufficiently small x, again here also x is small, the value of the polynomial depends upon the smallest term, lowest term of x power. Okay, how? That will be the result, and this is the result. Now I will do the proof. We take that ax raised to m common outside, so again we will get these terms, right? These terms, by the same conclusion, this will be less than 1. So this part is positive. So it will depend upon this a into x raised to m. Okay. So see here, they have given you an example. So this the polynomial will depend upon this sign, right? So sign of polynomial will depend on this side, and there is a minus 2 is given, and this is x cube. So it will depend upon x being positive or negative, right? If this was x square, suppose this was x square, then we can definitely say it is a minus. The sign of polynomial is minus. Why? Because this will be always positive. So the second result is what? If when x is very small, if we have polynomials from degree we arrange it into increasing order, and what is that? The term with x coefficient which is lowest, the x. Okay, the lowest term containing x power will determine the sign of the polynomial, right? Okay. So now the last result. So the last result, here we are considering x very large. Okay. When x is very large, the sign of the polynomial depends upon the term leading coefficient, the highest value of x. Okay, x power n. We will consider the sign of the leading coefficient, not leading coefficient, leading term. Okay. Actually, again same result. If we arrange this polynomial in an descending order and take that highest leading term outside, common outside, this portion will be less than 1. So less than 1 also also it won't become like minus 2, 3 and all. Okay, it will be between minus 1 and 1 inside that one. So we will get this term positive and it will depend upon this. Okay, so these are the 3 results you will have to learn. The sign of the polynomial when x values are different. So see here this polynomial. So x power 5, it will depend upon this. Okay. For large value of x, if they ask for small value, then we'll here constant term is there. So it will depend upon the constant term. That will be minus. If constant term is not there, then by second we will say that it depends upon this small value. For large value, this. Clear? Now this theorem is not there for you, but we'll just understand this. So if the polynomial f of x has different signs for f of a and f of b, suppose this is a, this is b. If f of a is positive, then this will be here. F of b is negative, then this will be here. So some will be joining like this. So at some point it should give 0, right? There is a root between a b. Between a and b there is a root. That is the theorem. Okay, theorem you don't have to study the theorem, but just understand that this is not there in the syllabus. So a, b, if of f of a and f of b are different signs, then there is a root inside this, between this. Okay, thank you.